What's up, guys? Welcome to Danger Person Code. In this video, we're going to take a look at the binary search algorithm. So this is what you would think of as a fundamental algorithm, and it solves a very specific kind of problem. And that is where we are looking for a specific element in terms of its index location in a sorted list. So this really only makes sense in terms of the logic we're going to write for the algorithm if the list is already sorted. And so if you're looking for the index, right, there's a lot of ways that you can go about this. You could basically just initiate a linear search and you could just uh, iterate through the list one element at a time, right, until you find an element that matches whatever element, whatever value you happen to be looking for, and then you could just return the index, right? Uh, the thing about a binary search, right, as opposed to a linear search, which is what I just described, is a binary search will do this in log n time, whereas what I just described, a linear search, will do it in n, O of n time. So if you get into an interview and somebody asks you to find and return the index of a specific element in a sorted list in log n time, they're talking about a binary search. Binary search algorithm will be what does this, which is, and that log n time is far more efficient in terms of worst case time complexity than O of n is. All right. But it is a little bit more complex, not terribly, but let's just get started. We'll see. So the binary search algorithm accepts an array, and it'll also accept some target. We'll just represent that for now as k. And then it will return at a base minimum, right? Either the index of the element, right, as it exists in this sorted array, or it'll return some indication that the element is in fact not in the array. Okay. So the very first thing that I'm going to do is I'm going to define two different pointers called left and right. Okay. So left and right will define in the beginning, right, uh, and throughout the entire algorithm, really, the search area. Okay, it'll define exactly what the search area, the area of interest actually is. And that's really how this works, is that we will keep defining and redefining what that search area is. We'll keep making it smaller based off of information that we have about the element in comparison to the midpoint of this search area. And we'll just keep squeezing that element until we find it, basically. Okay, and we'll see how this works. So left and right will initially be sent to 0, and the length of the array -1. And this will allow us to point at the very beginning, right, left and right at the very first element and the very last element. That's what this is. This represents the common syntax if we want to grab the index of the very last element in an array. Okay. So now that we have those pointers set up, I'm going to initiate a while loop. So that while loop will run so long as left is less than or equal to right. So they can be pointing to the same element. That's fine. The while loop will stop, however, if left ever crosses right. Because if left ever crosses right, essentially what that implies is that we have squeezed this search area as tight as it possibly can be squeezed, and we didn't find anything. It implies that the element is not in the list. Okay. So long as left is less than or equal to right, and then I will define some conditionals that check a few things. So the first conditional that we will check for every iteration of the while loop will be, so I'm sorry. The first thing that I will do is I will define a midpoint. So midpoint for this search area, which at first is just the entire array, will be left plus right minus left divided by 2, okay? And if you haven't seen this syntax before, right, this is how we define a division where we are also rounding down to the floor, so to speak, right, of whatever the answer is. It's a way of making sure that whatever answer this spits out is in fact an integer, and it will round down rather than rounding up. Okay. So now that we have this midpoint, and this midpoint will be redefined and reassigned every iteration of the while loop, so long as the while loop runs. Okay. So I will define some conditionals now. So the first conditional will be if the value at index midpoint for the array equals k, then we will return midpoint. So we could do like a fancy F string, that formats this and says, the value of k is located at the index midpoint or something like that, right? It's of course up to you, but we're just going to do the basic, the bare minimum of what this algorithm needs to return at this point, and it's just going to return the index where k is located. So we're just going to keep squeezing that search area until k is located at the midpoint. And if it never is, then it doesn't exist in the array. Okay, so the other thing that could happen is this does not equal k, but the value at index midpoint is less than k. So think about what that would mean. And think about, again, the fact that this is a sorted array. Okay, so they're all in sequential, and this is the array that we're going to be using, right? These are all in ascending order, right? From 4 on up to 40. So if the midpoint now is less than k, what that would imply is that k exists somewhere to the right of the midpoint, right? It would have to. If the array is in fact sorted, and this is also why this logic really doesn't work on an array that is not sorted. Yeah. Okay. So if in fact k is in the right side, right, or to the right of the midpoint, on the right side of the search area, whatever that happens to be for this particular iteration, well, then we need to redefine, right, these pointers, these left and right pointers again, right, to reflect that right half of the search area. No point in searching the entire search area anymore, right? We're just going to move to the right half of the search area where we know k to exist somewhere, right? If it does in fact exist. So what I'm going to do, if this is the case, is I'm going to take left and I'm going to reassign it to midpoint plus 1. So I'm going to take that left pointer and I'm just going to move it one place to the right of midpoint. So that now makes left and right the enclosures or the outward boundaries of a smaller search area, which really only includes that right half of the original search area, right? That is just one space to the right of the midpoint. The other thing that could happen, I could just do an else here, but just for readability, I'll do another elif, is that the value at index midpoint is greater than k. And if it's greater than k, because, again, the array is sorted, we would know that k has to exist somewhere to the left of midpoint, right? In the left half of that search area. So in this case, we're going to move the right pointer. I'm going to move it, as you might have guessed at this point, to one space just left of the midpoint. So midpoint minus 1. Okay. So it will run. It will run and run and run this while loop until this condition is true and we return the midpoint, or this condition right, causes the while loop to terminate. Okay. This condition basically stops being true, right, because the left has crossed over the right, and then we stop. And if that's the case, then we will return some condition, some return value that reflects that condition of the element not being in the list. We could return false, right? Common thing to do is to return -1. Okay. For now, I'm just going to return false. Okay. And let's try it out. But that is basically the binary search algorithm. Okay. And let's see how it works. So if we did our job correctly, when I call this on nums and I define some value, it should return the index of that value if it is in the list. So print binary search. Okay. I'm going to use nums as the first argument. And then I'm going to search for, let's search for 12. Okay. And 12 is at 0, 1, 2, 3. It's at index 3. And so let's run this. Okay. And there it is. We have returned the index of 12. Let's try it on something else. Let's try it on 30. 0, 1, 2, 3, 4, 5, 6. 30 is in fact at the index 6. And so it returns 6. Now let's put in a number that we know for a fact is not in this array. And we'll try 300. And it simply returns false. Okay. So just to recap, let me collapse this terminal a little bit so you can see the whole algorithm. Binary search algorithm will search for the index of an element in a sorted array. It will return that index if that element does in fact exist. And it will do that by sectoring off some search area with these pointers, which at first is just the entire array. And then while left has not yet crossed over right, it will define a midpoint right in the middle of that search area. And then based on how the midpoint value compares to the target value we're looking at, it'll keep redefining those left and right pointers to basically reduce the size and shift the position of that search area until we find this particular element right at the midpoint. And if we never do, then we just simply return false. Okay. And that is binary search algorithm. All right. If you have any questions, throw them up in the comments. Feel free to like and subscribe and join me in the future for more brutal, savage algorithms.